In this video, we're going to introduce linear systems of first order ODEs. We're going to introduce what writing an ODE as a linear system would look like. Now, we know that any model involving an ordinary differential equation, no matter how complicated, can be expressed as a system of first order differential equations. It may be necessary to define new variables as we go along to represent the derivatives of the other variables, but generally this can be done. If you've taken linear equations already, you know this is basically a linear transformation. We will assume the system of first order differential equations in n unknown functions, x sub 1t, x sub 2t, x sub nt, which are the unknown functions, can be written explicitly in terms of the derivatives of the n dependent variables. That is, we can write it in this form. X sub 1 dt of f sub 1 t, x1, x2, all the way x sub n. The derivative, the first derivative of x sub 2 with respect to t can be wrote as f of 2, same kind of thing. And the derivative of x sub n with respect to t is f of n. That should be f of n, not f of 2. F of n with the t all the way to x sub n, where the f1, f2, fn are arbitrary functions of t, x1, x2, x sub n. Any single order nth differential equation, single nth order differential equation of x sub n is equal to f, t, x1, or x prime all the way to x sub n minus 1 derivatives can be expressed in the form of a single system by defining new variables x sub t and its derivatives up to the order of n minus 1. Let's give you some definitions. If each function f sub I of t, x1, x2, xn of x sub n, where I is 1 to n, then the above equations are linear dependent in x sub I variables. That is, f sub I of t x sub 1 to x sub n can be wrote as a sub I1 x1, a sub I2 x2, all the way up to a sub I n x sub n plus bi. Where a sub ij and bi are arbitrary functions of t, then the system can be called a linear system and is an n-dimensional linear system, first order differential equations. And it will be of the form x sub 1 prime is equal to a11 x1, a12 x2, all the way up to a sub n x sub n b1, x prime sub 2, a21, and of course this looks like, I don't know about you all, but this looks like a11, a22, and all that looks like the positions in a matrix, where these of course would be our constants. If b sub I of t is all equal to 0, then this is a homogeneous linear system, and the number of n equations is referred to the dimension of the system. So as an example, we're going to write an equivalent first order system in the form given above, determine the dimension of the system, and state whether or not it is linear, and if it's linear, whether it's a homogeneous system or not. Now, this is similar to what I did when I had to use my GeoAlgebra. Now, remember when I was using my GeoAlgebra, I had to use y. X prime of t was y. Do you remember that from our last video? And then I said, oh, y prime is equal to x double prime. So the first thing we're going to do is something really similar. I'm going to say x sub 1 prime is equal to x sub 2. Nice, easy way to start out. That means x sub 2 prime is equal to the sine of t minus 2x sub 1 minus 5x sub 2. And you're thinking, how did that happen? Well, if we take the fact that x sub 1 prime is equal to x sub 2, then x sub 1 double prime must be x sub 2 prime. Oh, that means this can be replaced with x sub 2 prime plus 5. My x sub 1, or x prime, was x sub 2, so that's 5x sub 2. My x is just going to be x sub 1. So So I have plus 2x sub 1. This still equals the sine of t. So if I solve for x sub 2 prime, I'm going to end up with the sine of t minus 2x sub 1 minus 5x sub 2. So here are my two equations that I have. It is linear, right? We are linear because I have no x prime squared. I have no x's squared. My thing that is the sine is a function of t alone. It's not homogeneous because I have the sine of t. And it's a dimension 2 because I ended up with two equations. So that's a non-homogeneous linear dimension 2 system of equations. Now let's take a look at my next example here. Now going right out of the gate, I know it's non-homogeneous because of this t. So I know that's non-homogeneous. So the first thing I'm going to do is say, okay, well, let's let x sub 1 be x. Let's let x sub 2 be x prime, which is then x sub 1 prime. And let's let x sub 3 equal x double prime of 1. Well, x double prime, which is x double prime of 1, which means it's x prime of 2. So then I have x sub 2 prime is equal to x sub 3, and then x sub prime of 3, which would be equal to, well, let's go back up here. X double prime, x prime, prime, that's this one, the third derivative, which means x prime of 3 would be the third derivative of x, which is the third derivative of x sub 1, which is x prime of 2. That means x prime of 3, which would be taking this and solving for x triple prime, negative 4x double prime, plus or minus 3x plus 2 plus t, then gives us x prime of 3 is equal to 2 plus t minus 3x. 3x is x sub 1, 3x sub 1, and then minus the 4x double prime, which was x sub 3. So minus 4x sub 3. And so I have linear, because all of my x's are linear. It is not homogeneous because we talked about that before. It was a t, and it's a dimension 3 because I need these three equations. See, I know it's homogeneous right out of the gate. I don't have to do anything hard with that. Homogeneous. All right. X sub 1 would be y. That means x sub 1 prime would be x sub 2, which is equal to y prime. So then I have basically, let me see, solving for y double prime, which would be x sub 2 prime, which would be equal to, well, I have to divide everything by 2 and move things to the other side. So it'll be positive 5 over 2 y prime minus y over 2. Now I'm going to go ahead and do my replacements. My y, 5 over 2y, which is x sub 2, this becomes 5 over 2 x sub 2, minus my y, which is x sub 1 divided by 2. So these are my equations. If you got lost, let me give you the equations. My equations are x sub 1 prime is equal to x sub 2. X sub 2 prime is then equal to 5 over 2 x sub 2 minus x sub 1 over 2. Those are my two equations. Now, let me see, what else? So I should say this one up here, because it's all in primes, I should say that x sub 1 prime is equal to x sub 2. Those are my three equations because I'm doing x sub 1 prime, x sub 2 prime, x sub 3 prime, x sub 4 prime, or however it needs to happen. Now this is homogeneous, it is linear, it is a dimension 2. Now let's take a look at D here. So once again, I got to figure out what I'm going to do as replacements. Of course, x is a good replacement for x sub 1. That means x sub 1 prime would be a good replacement for x sub 2. X sub 2 prime, which is x sub 1 double prime, which is x double prime. And then x sub 2 prime would be a good replacement for x sub 3. So we could say this is x sub 3. Now, x sub 3 prime would be x sub 2 double prime, which would be equal to x sub 1 triple prime, which is equal to x triple prime. And I'm going to label this x sub 4. So now I've got all my primes in terms of my derivatives. So my first equation is x sub 1 prime is equal to x sub 2. X sub 2 prime, which is equal to x sub 3, x sub 3 prime, which is equal to the x sub 4, and the way I find that is I come back up here and I say, wait, let's go ahead and do these replacements. This is going to be equal to x, which is x sub 1. X sub 1 prime is x sub 2 squared, and then minus t, x double prime, which was x sub 2. Whew. So these are the three that I have. This is nonlinear because of this x sub 2 squared. It is a dimension of dimension 4, because look how I had to go to the fourth derivative. Ooh, I do need to put in my x sub 1 is equal to x. So it is a dimension 4, and I have my 4 equations. It is nonlinear, and it is homogeneous because I don't have a function of t alone. Now let's look at E, where I have x prime is equal to xy, and I have x or y triple prime is equal to x plus x prime plus x double prime. Again, we start out with x sub 1 is equal to x. We like that one. X sub 2 this time is going to make this y because I have x and y. And then I have x sub 3. A good choice for that would be x sub 2 prime, which is y prime. And then I have x sub 4, which is equal to x sub 3 prime, which is equal to x sub 2 double prime, which is equal to y double prime. Now I've got a replacement for this. I have a replacement for this, and this, and this, and this, and this, and this. And so what I've got are my equations are x sub 1 prime is equal to x sub 1, x sub 2. That comes from right here. X sub 2 prime, which is equal to x sub 3. That's nice. X sub 3 prime, which is equal to x sub 4. And then x sub 4, which is equal to x, which is x sub 1, plus, and this is where I'm getting it right here, plus x double prime. Well, x double prime, or excuse me, y double prime was x sub 4. And this should be x sub 4 prime. Let me get everything in the right places. And then plus y squared. So plus x sub 2 squared. Again, nonlinear. Bam, because of this part. It is of dimension 4. And it is not homogeneous because of the fact that I have x. I could isolate my y's and my y double primes to the other side, but my independent variable in this case is x. So it is non-homogeneous. Let's take a look at my next example. I have 2x prime or 2y prime minus x prime is equal to x plus 3y, and x prime minus y prime is equal to 2x minus 5y. First thing I'm going to do is I'm actually going to add these two equations, and I'm going to write them in the correct order. So I'm going to do negative x prime, so negative x prime plus 2y prime is equal to x plus 3y. And then I have x prime minus y prime is equal to 2x minus 5y. Now I'm going to add these two together. When I do this, I get y prime is equal to 3x minus 2y. Now, my systems are straightforward and pretty darn easy. I'm going to have x prime is going to be equal to 5x minus 7y, because y prime is going to be equal to 3x minus 2y. So the two systems right here, it is linear, it is homogeneous, and it is a dimension of 2. Now you're thinking, where did this x prime from? Well, once I know what y prime is, I can plug it into one of these two equations. This would probably be the easiest, y prime being 3x minus 2y. So x prime minus this quantity, 3x minus 2y, is equal to 2x minus 5y, which is where this comes from. Now, here's an application. You are given a mechanical system with 3 springs, A, B, and C, and 2 objects, F and G, and a mass of M. Springs A and C have a spring constant of K, and spring B has a spring constant of 2K. The equilibrium positions of all the elements in the system are shown in the diagram below. The spring C is attached to the right end of the platform. Write a system of first-order differential equations for the displacement x sub 1t and x sub 2t of the masses F and G, respectively. So we know that k sub 1, in this case, k sub 1 right here, and k sub 3, because they tell us from up above, that the springs A and C have a constant k. So we know that k sub 1, which is equal to k sub 3, which is equal to k. And we also know from up above, it tells us that k sub 2, this is this middle one, is equal to 2k. Now, they also tell us that F and G have masses of M, so M sub 1, which is equal to M sub 2, which is equal to M. So that's kind of nice. Then, the force on the left mass, which is this one, we'll start with this one, I'll even do it in yellow, of M x sub 1 double prime is equal to negative k x sub 1 plus 2k x sub 2 minus x sub 1, which is equal to k, and I get negative 3x sub 1 plus 2x sub 2. Now, I'm using the formulas for springs, and this comes from previous videos, or you can look it up in a physics book. Now, the mass on the second one, which I'll do in blue, so I have m of x sub 2 double prime, which is equal to negative k x sub 2 plus 2k x sub 1 minus x sub 2, which is equal to k 2x sub 1 minus 3x sub 2. Because this is a second order, and I know it's a second order because it's a second derivative, I'm going to need the first replacement, which is x sub 1 prime, which is going to be equal to x sub 3. And x sub 2 prime is going to be equal to x sub 4. Now, the reason I'm using these subscripts is simply because I've already got subscripted x1 and x2. So then what we get is I have x sub 1 prime, which is equal to x sub 3. I have x sub 2 prime, which is equal to x sub 4. That means x sub 3 prime, which is the derivative of x sub 1 prime, would be equal to, solving for the x sub 1 prime, or x sub 1 double prime, would be equal to k divided by m multiplied by negative 3x sub 1 plus 2x sub 2, and then x sub 4 prime, which is equal to km 2x sub 1 minus 3x sub 2. So here's my equations. It's a second order because of the double prime. But what is the dimension of the system? The dimension of the system is 4 because I needed 4 equations to describe this system. So it is a dimension of 4. Now, the question is this system linear? And the answer is yes, because all of my x sub 1s, x sub 2s, all of them are linear. There's no x sub 2 squared, there's no x sub 1 squared, there's no x sub 3 squared, x sub 4 squared, none of those. This is linear and the answer is yes. Now in our next video, we're going to explore solutions. This video is all about setting them up, and that's it for this video.